Alright, so here's example 11 for probability. We need to find the probability that a random multiple of 2 chosen is a multiple of 3, a random multiple of 4 chosen is a multiple of 7, and a random multiple of 43 chosen is actually a multiple of 47. And then we can generalize this for the probability that a random multiple of x chosen is a multiple of y, where x and y are relatively prime natural numbers. Let's just work for part 1 of part A. We can write the first several multiples of 2. So it'll be 2, 4, 6, 8, 10, 12, and so on. I'll perhaps stop here. And notice the multiples of 3 here will be 6 and 12. And the thing that you can infer from this is that the multiples of 3 in the multiples of 2 occur 1/3 the time. So it will occur once every 3 multiples of 2. And another way to prove this or visualize this is to use mod congruences or modulo, I would say. Modular arithmetic or whatever you would call that. So let's just suppose the number we've chosen is n and ensure that n is congruent to 0 mod 2. With this, the possible values of n mod 3 or mod 6, I would say, will be 0, 2, and 4 mod 6. And notice n is congruent to 0 mod 6 is the value that we've wanted in this question. Hence, our probability will be once every 3 times, since we have two other possible choices with a total of 3. We can do the same technique for part 2. We can write the first few multiples of 4, or perhaps I'll skip a bunch of them. We can stop at, for example, 28, for example, and then we can continue to 56. Now, I've skipped some of these because 28 and 56 are the numbers that satisfy our criteria. And you may notice that the number of multiples of 4 behind or before 28 are 7. So there are 7 multiples. And another thing that can infer from this is that the multiples of 7 in the multiples of 4 occur once every 7 times. So it is repeating in a pattern, I would say. You can actually prove this by using the modulo technique for part 1. So hence our probability for this question will be 1 over 7, since it occurs once every 7 times. Okay, now for part 3, another similar one. And let me just write for this year, let me skip that to, let's say, 2021, which is the year that I'm uploading this, by the way. And then we can skip this all up the way to 4042, for example. Notice that I picked these specific numbers because these numbers are actually the numbers that are a multiple of 43 and a multiple of 47 simultaneously. And you may notice that there are 47 multiples of 43 behind every multiple of 2021. So again, by the same reasoning, we can conclude that the probability here will be 1 over 47. Which again could be visualized or proven by the modular technique before. And let's just try to generalize this for some arbitrary, relatively prime natural numbers x and y. So first, let me just write the multiples of x, which will be x, 2x, 3x, all the way up to, let's say, xy. And after that will be 2xy. And after that will be 3xy and so on. Now, pay attention to this right here. notice that the first multiple of both x and y appears here, which is xy. And then notice that there are exactly y multiples of x behind our or before our first multiple of x and y. So we can conclude that our probability here will be once every y multiples of x. Since it occurs once every y multiples of x, so we have x, 2x, 3x, 4x, all the way up to we arrive at xy, which again could be proven by our modular technique that we have done before. Or perhaps let me just do that. So suppose our number chosen is n, and this is congruent to 0 mod x. Now for n congruent xy, there are y possible values for this, which will be 0, x, 2x, 3x, all the way up to let's see, y minus 1x, because y-axis will be just be congruent to 0 again. So this repeats in a cyclic pattern, and this is why we can use this technique of this thingy. So here, since 0 is our wanted value, our probability here will be, once again, 1 over, there are y possible values for n mod y, n mod xy, I should say. And with this ends this video.